Hi everybody, uh, welcome back. So, we will continue with our routing algorithm. Uh, I guess we talked about the Dijkstra, then we talked about Bellman-Ford, in between we talked about flooding. So, these were the three routing algorithms which we were. So, even before going, I think I rushed through this count up till infinity problem. So, count up to infinity, let us just brush this. This is important. So, let us just brush it. So, what does count up to infinity means? I wrote it last class, I think, that we understand good news fast, but bad news slowly. Okay, we understand good news fast and bad news slowly. So, if you just go back a bit and see this thing once more, that what we have initially say A, B, C, D, E. We have A, B, C, D, E where all are connected. So, this is the LAN connection. Okay. This is the LAN connection. So, 1, 2, 3, 4. So, E is at 4 hop, while D is at 3 hop, C is at 2 hop and B is at 1 hop to A. Okay, fine. And all the lines, so what is happening is all the lines are actually passing through A. All the lines are actually passing through A. So, then what happens? Now, A goes down. So, as soon as A goes down, what happens? B is periodically checking, okay, and B finds. So, B gets input from A, C, D, 3, D, E. So, it does not get any input from A. So, this is infinity. It gets input from C, which is 2. It gets input from D, which is 3, and it gets input from E, which is 4. So, then what happens? Then we are taking minimum of alpha infinity 2, 3, 4 and this becomes 2. So, now here I write 2. So, now for C what is happening? C is getting from B, it is getting 2, from D it is getting 2, from E it is getting 4. So, what happens? So, minimum plus 2 plus 1, so sorry. So, this becomes 3. Okay. So, for D it is getting 3. So, this becomes 3, sorry. So, now for C it is getting 3 from C, it is getting 3 here and 3 here. I am sorry, you will not get this 2, you will just get A and C, 2 neighbors of B, and neighbors of B is giving alpha infinity and this is giving 2. So, then B will be minimum of infinity comma 2 plus 1. So, that is 3. So, here 3 have put. Now, C has 2 neighbors, one is B and D. So, B and D are 2 neighbors. So, what is happening? So, B is also 3 and D is also 3. So, then C will what write? 3 plus 1, 4. So, this writes 4. Now, D has 2 neighbors, C and E. So, both have 4 and 4. So, we will write 5 and E has one neighbor D which has 5. So, it will write 6. Okay. So, now after the first round, what has happened? B has become, what is B? B's distance from A has become 3, C's distance from A has become 4, D's distance from A has become 5, while E's distance from A has become 6, fine. But what is the exact distance? What is the real distance? What is the real distance which we have? The real distance is actually infinity. The real distance is actually infinity. Okay. B, C, D, E, this is 3, 4, 5, 6. But real distance is actually infinity because C's original 2. How did C's original 2 come? From B, 1 up to B and 1 up to E. There is no other path, but B does not understand that. Okay. B does not understand that. So, B does not understand that. So, that is why B thinks what? B thinks that C is following some other path. Okay. So, everybody is confused. So, C thinks B is following some other path. So, that is why B becomes 3 and C thinks B's now latency has increased. So, it becomes 4. D thinks that C's latency has increased. So, it has become 5, 6. So, then again what will this become? 5, 6, 7, 8. Okay. Because it is infinity and 4. So, it will become 5 next round. Then it will become 7, 8, 9, 10. So, what is happening that the latency is slowly increasing. Okay. What we need is immediate information that A has gone down, immediate information that A has gone down, and we should A has gone down and we should uh, think, or we should think that line is open and put infinity value to all the rows in the routing table, all the A rows in the routing table. So, what we want, this to be infinity, this to be infinity, this to be infinity, this is what we want. But how is this infinity coming? Very slowly, it is coming 3, 5, 7, 9, slowly infinity. Infinity will come, but after a very long time. That is why we are calling it counting up to infinity. So, we are slowly counting and going up to infinity. Okay. So, this is a very important problem which Bellman-Ford's, which shows Bellman-Ford's weakness. Okay. So, next thing which we should know is the flooding algorithm. Okay. So, flooding, I see there are many questions that what is the difference between flooding and broadcasting. So, this question has come again and again. Many people ask that what is the difference uh, uh, what is the difference between flooding and broadcasting? What is the difference between flooding and broadcasting? So, if we see that flooding is, if you have a network like this, say something like this network. Okay. So, you are flooding the entire network. Okay, and with known and unknown IPs. You really don't know all the IPs, you are broadcasting. Your flooding means you don't have any idea about what the IPs are there, and you are actually broadcasting the entire thing. So flooding is basically a discovery protocol. Discovery protocol. So here the IPs are not known. Okay. While in broadcasting, the IP set to whom one should broadcast, one should send is known. Okay. IP set to whom one should send is known. So, this is a more structured protocol, we'll talk about this also, whereby if you think this is a more structured protocol, whereby you can have several efficient algorithms. Why you can have several efficient algorithms? Because you can actually use the routing table, use the intelligence or the information from routing table, while in flooding you actually don't know the entire network. So, you have to flood the entire network. Okay. So, also just to tell one thing, we are now talking of flooding at IP layer or network layer. This discussion is flooding at network layer. And how are we actually stopping flooding? Because we have the routing table, that is why we do not need flooding. But in which case we will surely need flooding? In which case we will surely need flooding? Specifically in the MAC layer. So, if you remember, I told that if two are IP neighbors, these are two machines which are IP neighbor, there may be a lot of layer 2 switches in between. Okay. There may be a lot of layer 2 switches in between. So, this is a layer 2 network. Okay. And since a layer 2 network, so IP layer 2, you have this layer 2 network. Okay. Layer 2 network, here there is no routing table. Here there is no routing table. So, how will communication go inside this network? This network luckily is a smaller network. This will not be an internet scale network, but how will communication go inside this network? It will go through the flooding protocol. Okay. So, flooding is widely used in the MAC layer. Okay. Flooding is widely used in the MAC layer instead of in the IP layer. We try to avoid flooding, we do broadcasting. I will talk about flooding and broadcasting in details. So, now we have understood the status of distance vector routing. So, distance vector routing has this problem of count up to infinity. So, and what we know, when will distance vector routing work? Then when will it work well, very well, when there is minimum failure. Okay. when there is actually minimum failure. But in real internet situation, churn is very high. Okay. In real internet situation, churn is very high. So, distance vector routing will not work. So, then we will shift to link state routing. Okay. So, which we are doing next. So, what is link state routing? Link state routing is a variant of Dijkstra algorithm. Okay. It is a variant of Dijkstra algorithm, which is actually, it is a variant of Dijkstra algorithm which is run in each individual node. Okay. So, it is a variant of Dijkstra algorithm which is run in each individual node. So, if we have to run the Dijkstra algorithm in each individual node, then what do we need? What are the inputs which are needed? Okay. So, what does Dijkstra algorithm need? Dijkstra algorithm needs a graph and the weights of that graph, of the edges in that graph. Okay. Of the edges in the graph, if you remember. So, this is what Dijkstra algorithm actually does. Memory, this is what is Dijkstra algorithm, where you have a graph and every link has some weight. Okay. So, that has to be actually received by every node, that has to be received by every node to run Dijkstra algorithm, that has to be received by every node to run Dijkstra algorithm independently. So, that is fine. So, then what are the challenges? What are the challenges we will face when we have to do something? So, one challenge which I can immediately think, is having consistency. So, it is how to have consistency in result or in acquiring data, because what, some data means link information may be old. Okay. So, we have to check all these things while we are building the link state algorithm. So, let us go to link state algorithm step by step. So, what is link state routing telling? That each router has to do what? One, discover its root member and learn their network addresses. So, one, discover and learn. Okay. So, I have to know what are my neighbors and what are the network address. So, how will I do that? I will do some sort of limited flooding. Okay. So, one question which so I am talking about link state routing, which is taking the entire topology into consideration. So, let us see this once more. So, one important question about flooding is, so when you begin to flood, what are the consequences? When you begin to flood, What are the consequences? The consequence is that the packets can go from node to node forever. Okay, packet can go from node to node forever, which is, if the packets go from node to node forever, that means the entire network will get congested. Okay, will get congested. So, in order to stop that, there is something called TTL. So, each packet has a value of time to live, and this value gets decremented by 1. This value gets decremented by 1 every time one a packet hops from one node to another. With this, let us come back to link state routing. Let us come back to link state routing. So, link state routing, first step is discover. Okay. Second step is set the distance or cost matrix for each neighbors. So, set the distance or cost matrix. Okay. How will we do that? We can do this dynamically, or we can do it adaptively, that we can understand, we can see how much bandwidth, okay, we can see how much bandwidth, or we can see how much time is taken to travel from one node to another. Okay. Third is construct a packet telling all it has learned. So, I will come to this. Send this. So then we construct a packet. We construct a packet of its neighborhood. Construct a packet of its neighborhood, and then send this packet to all other routers. Okay, send this packet to all other routers and compute the shortest path on every other router. Okay. So, you send this packet, then every router will then generate the graph and then build up the shortest path algorithm. So, these are the 5 steps which are taken. So, let us go again step by step. So, learning about the neighbors. So, learning about the neighbors, there are some small issues which are there, that inside a LAN, if you see inside a LAN, okay, what you see inside a LAN? Inside a LAN, there is basically multiple nodes which are connected to the same LAN. There are multiple nodes which are connected to the same LAN. So, how to determine neighborhood of A, B and C, A, B and F. If you see in the figure, there is A, C and F, sorry, A, C and F, we have D, E, G, I, H. So, in order to do this, what we think, a LAN as a independent node. LAN is an independent node, and this way we construct the neighborhood. Fine. Now say, sorry, now say this way you construct the neighborhood, fine. So then what happens? So then what happens when you are constructing the neighborhood, you will get, so A will understand, or say C will understand who are the neighbors, that D, E and N. If N is the neighbor, then actually A and F are its neighbor, okay. Or H will understand that G and I is its neighbor. So H understands G and I is its neighbor, okay. So now everybody understands, H I understands, B understands, D and C is its neighbor, okay. Okay. C understands A and F and D and B is its neighbor, okay, fine. And A understand, so I am sorry, this was not B, this is E, sorry, this is E. So B understands A is its neighbor. So how are they understanding? By the simple ping, okay. If you can ping and see which are your neighbors, you get the neighbor list. Now you have to construct, or you have to set linking cost, that how much is the cost between B and D, how much is the cost between D and E, how much is the cost between C and. So cost can be, actually I told you, cost can be done it two ways. One is the bandwidth, what bandwidth we are using, are we using 2 GB bandwidth or 2 MB bandwidth, accordingly we can determine cost one, and also we can check the delay and see how much is needed for a packet to go to that link and come back to that link. So, go to that link and come back to the link, and we send a special echo packet, okay. So, this is setting link, okay. So, now once you have set this link cost, so this is the network, okay. So, this is the network A, B, C, E, okay. This is the network A, B, C, E, F, D, and who are neighbors of B? F and A. Who are neighbors of C? Who are neighbors of C? E and D. This is a different network than this network. I am just taking another network to make you understand. This is a different network than this network, okay. So, who are the neighbors of A? B and E, okay. Neighbors of B, A and C, okay. So, this way, and we have the cost. Now, see this, that we are getting, so we are getting A's. So, A, how are the link packets developed? See that A is developing, I have a link with B and that distance is 4, and I have a link with E and that distance is 5. Then B's packet is developed, who are the neighbors of B? C, A and F, and this is like 4, 2, 6, okay. This is like 4, 2 and 6. C's neighbors are B, D and E, and this is 2, 3 and 1, okay. Similarly, D's neighbors are C and F, and this is 3 and 7. So, in this way, every node, what has happened? Every node prepares their every node prepares their own linked state packet, okay. So, every node prepares their own link state packet. Now, what do? They send it to other nodes. So, now again think that after certain point, say node A will have all these 6 packets. So, node A has all 6 packets, fine. From there, node A now can reconstruct the graph. So, node A can reconstruct the graph, and what can it do? Then it can run Dijkstra, okay, reconstruct the curve, run Dijkstra, and reconstruct the graph, run Dijkstra, and build the routing table. Okay. So, this is in straightforward. Just let us see what are the challenges. So, let us just try to understand what are the real challenges. Okay. So, if we go a bit, number 1, the few problems. One is what is happening? Say this process is going on continuously. Process of link state packet creation and exchange. Link state packet creation and exchange is actually going on continuously. Okay. So, link state packet and exchange is going on continuously. So, that means what? What does that imply? What does that exactly imply? What does that exactly imply? That exactly imply is that exactly implies that for each packet generated by each node, one has to give a sequence number. Okay. For each packet generated by each node, one has to give a sequence number. And then what can happen? So, you will give sequence number 1, 2, 3, and then it will somehow hit some x, and then again you have to give 1, 2, 3, 4. Okay. Now, why is the sequence number important? Just let us think, why is this sequence number important? Because say I get a packet with, say take this again, I am say node C. Okay, I am node C. Fine. I am node C and I get a packet of node A with sequence number say 15. Okay. Then after say 10 seconds, I get a packet with sequence number say 14. What will I do? So, I get a packet with sequence number 15 and I get a packet with sequence number 14. What will I do? So, I will immediately understand that 14 is a older packet. Okay, 14 is a older packet. So, I will discard 14 and keep 15. So, that is why sequence number is important. Then the sequence number has to come, but what is the problem? The sequence number slowly can get exhausted, and then you have to wrap around. Say if your system gives 15 sequence number, so then 1 2 3 up till 15, and then the next sequence number will be 1, but in essence 1 is newer than 15, which C will not understand. So, this is a problem. Okay. How to solve this problem? So, how to solve this problem? The problem solving is simple, that if you take a big sequence number, okay, if you take a big sequence number like a 32-bit sequence number, if it is a 32-bit sequence number, let us think when it will wrap. 32 sequence number means how many numbers can come? 0 to 2 to the power 32 minus 1. Okay, 2 to the power 32 minus 1, and say how you are updating after every 10 seconds. So, then how many updation in a minute? 6, and how many in an hour? 60, and how many in a day? 24, and how many in a year? 364. Okay, 365. So, how much is that? So, you see 663,600 into 24 into say 500. Okay. So, into 20 into 500. So, this is how much? 10,000. Is it 10,000? 10,000. This is something around this. So, it is something around this. Okay. It is something around this, which is much less than this, and it will take 137 years to wrap. So, we are solving that problem. The second problem is, yeah, so we need the H field. So again the second problem would again make you a little more aware that why we need the H field. So, what is happening now? Say there can be 2-3 things. The root crashes, the router crashes. So, the entire sequence number can get lost, or the sequence number can get corrupted. Okay. The sequence number, say sequence number, take a sequence number, I have a 4 bit number. Okay. So, 4 bit number, one number is 00001. If one bit gets corrupted, it can become 1001. So, from 1 you are suddenly becoming 9. Okay. You are suddenly becoming 9. So, then every other packets which will be generated between 1 to 8 will be discarded wrongly. Okay. So, luckily every packet has a TTL. So, luckily every packet has a TTL. So, after some time this packet would get discarded and the problem would get solved. So, aging the packets is a very important thing, that we should age the packet and slowly let it die, otherwise it. So, see, one important thing which we must remember, that this is a very distributed system. So, if we keep things loose ends, the havoc it can do, actually we also cannot perceive many times that what are the havocs it can do. Okay. So, you are aging and so these are the problems. So, now see what is happening. Now, ultimately I have talked about the problem statements, but ultimately what has happened, B has got all these 6 informations. Okay. B has got all these 6 informations, all this 6 nodes information. So, now how will B write? See, how will it be right? Say B has a writing that A, source A, it has come. Okay. How is okay? Let us have the network also. Otherwise, it so just you can. I hope you can see this part, the network part, or I will draw it a little bit bigger so that both becomes visible to you. Okay. So A, B, C, D, E, F. It was like this. Okay. Am I right, or is there is the sequence right? Okay, fine. A, B, C, D, E, F. Fine. So now see A from A is sequence number 21. A is sequence number 21, and it has immediately come. So age is 60. So age is 60 means if I am reducing the age after every 10 seconds means how much time it will stay? It will stay for like 10 minutes. It will stay for 10 minutes, and now this is. So what I have to do? I have to distribute this packet to everybody. So remember that I have to distribute this packet to everybody. So if I have received from A, if B has received from A, to whom A they should it should distribute to C and F. Okay, because C and F is, I hope you can see this, that C, so it has to distribute to C and F. Check here, it has to distribute to C and F. Okay, because C and F are actually neighbors of B, and from where it has got the packet? It has got the packet from A. So to A, it should send back a acknowledgement. Okay. So this is send flag and this is acknowledgement flag, but it can see it. See, you may ask that it will receive packet from one only. Will it receive packet from multiple places? It can receive. See E. Okay, if you consider E, what happens is E is actually receiving the packet from both. E's packet is received. E's packet is received by B. I am seeing the, so to be clear, this is B's view. This thing is B's view. See the packet buffer for router B in the previous slides. Okay, it is the packet buffer for router B. So I am seeing B's view, and B has received E's information. E's information, how has B received E's information? From both F and A. See F and A. See F and A. It has received information from both F and A, and if has received from F and S, that is why it has also got decremented by 1, that at first time step it has received either from A or F, and it has the next time step it has received from F. Okay. First time step it has, let us assume first time step it has received from A, and next time step it has received from F. Okay. And so now it has to send to only C. Okay. Now it has to send to only C. Okay. So this also happens with D. Okay. D's information is received through C and F, and so it has to send this information back only to nobody else. Okay. So then what is happening through this? You are stopping flooding, and sending packets. So there are 2-3 things which is happening. We take latest version. Okay. So this way what is happening is we are ensuring that we are ensuring that there is no inconsistency. So, through this we are actually ensuring that there is no inconsistency. Fine. So, I guess now let us once more time go back and look into listed routing before uh, stopping this session. That linked state routing is basically doing a Dijkstra algorithm. Just let me think, it is basically doing a Dijkstra algorithm. It is basically doing a Dijkstra algorithm, but in order to a Dijkstra algorithm, what has to be done? Every node has to get the end, and it is running a Dijkstra algorithm on every node independently. It is running a Dijkstra algorithm on every node independently, and in order to run that, one has to, if I have to run the Dijkstra algorithm on every node independently, what we have to do? We have to do a simple thing. We have to get the entire graph to every node, and in order to get that entire graph to every node, what is the basic unit which every node is actually sending to other nodes is a linked state packet. And once you get the linked state packet, there are some things which consistency check which one has to do, like one has to check that whether it is a old packet, it is a multiple packet which has been sent by two sources, etc., etc. And once those simple consistency check is done, then it stops the nest, then it sanitizes, build up the graph and constructs the Dijkstra and construct the routing table. Okay. So, one question which you can ask is that this is a costly process. This is a very costly process because every node has to take information of every other node. There has been some questions. One is that again the sequence number question has been there. Sequence number, how is it corrected? The sequence number is if a router fails, say if a router fails, okay, if a router fails, then it forgets. So, if a router fails, then what happens? It completely forgets the previous sequence numbers. Okay. Router fails, completely forgets the previous sequence number. Okay. Then what happens? It will start from 0. Start from 0. Okay. So, now there is, so some packets have higher sequence number, some packet has higher sequence number and some has some will have now lower sequence number, after now lower sequence number, okay, after the crash, because the sequence number has started from 0. So, some numbers may be 15, 30, 16 and some may be 0, 1. So, there is some discrepancy in the system. Okay. There is some discrepancy in the system that will stay, but slowly these packets will die, will age and die. Okay. Slowly these packets will actually age and die. So, these packets will age and die, then again the entire thing will become refresh. So, sequence number can get disturbed, but as soon as the packets get the older packets die, then again things will get restored. So, if there is a crash, there can be some intermediate state when there will be discrepancy. So, intermediate state of discrepancy. Okay. This will stay. I will most probably start writing the spelling of discrepancy wrong. Okay. A, this one. So, discrepancy state, intermediate state of discrepancy. Okay. Then it will become fine. I guess I have answered the question. Uh, so, ping is again ping is a high level protocol. Okay. It's a application layer protocol. Okay. So, which this is a one year, it's a protocol like FTP, like SFTP. This is also a protocol. Okay. So, this from distance vector routing, here ultimately all these routing algorithms, what are they producing? They are producing a routing table. They are producing a routing table, and what is a routing table? Are we producing a stateful routing table or a stateless routing table? We are producing a stateless routing table. We have told that last class that we are producing a stateless routing table because IP is connectionless protocol. Okay, if you remember. Okay, so IP is connectionless protocol. That means what we have, if destination and next hop, there are two things that if you want to go, say I am keeping something in node B, a routing table. That means, if you want to go to destination A, then what should be the next hop? Next hop can be X. If you want to go to destination C, what would be the next hop? Can be Y. If you want to go to D, what would be the next hop? Maybe Z. So, these are the two things which you are keeping, and all these algorithms are ultimately producing this. It is taking input graph and output routing table. So, we come from, so there is this example protocol. So, this is a basic protocol, but this example protocol is more popular protocol is OSPF, open source shortest path. Okay, open source shortest path, which is used, which has a underlying link state routing algorithm inbuilt. Okay, which has a underlying link state routing inbuilt. Okay, and then you have ISIS, which is not so popular, but ISIS actually supports multiple network layer protocols at the same time, that it can be IP, IPX, AppleTalk, all sorts of layers, but although it has this facility, the issue is that ultimately we work on IP. So, all this other type of layered facility is not so useful. Okay. So, then normally I will talk about this a little more sometimes later, that OSPF is the protocol which is followed, okay, and which takes into consideration IP and works. So, one problem which you may have you may understand, or you may think, or you may have realized that routing, we are trying to make a routing table with all the nodes who are there in the internet, which may be very difficult, because then you have to scale hugely, that if there are billion nodes, you have to have billion entries in the routing table. So, billion node will have billion entries, which we don't want. So, that is why the next algorithm is the hierarchical routing. So, the next algorithm is a simple algorithm which is a hierarchical routing algorithm. So, see what we can have region 1, region 2, region 3, region 4. So, you have region 1, region 2, region 3 and region 4 and region 5. Okay. So, now if I ignore the region, so we have region 1, region 2, region 4, region 5. So, one way of is ignoring okay. One way of doing it is ignoring the region. Fine. So, if we ignore the region, then what happens? This is a straightforward. There are nodes and we think everybody is connected to everybody, or we have to build up the routing table for every node. So, see that I am building up a full table of 1A. I am building up a full table of 1A. So, full table of 1A would include all the nodes 1B, 1C, see 1B, 1C, 2A, 2B, 2C, 2D, 3A, 3B, 4A, 4B, 4C, 5A, 5B, 5C, 5D, 5. So, all the nodes we have to build. Okay. But if I have a hierarchical version, then which are the nodes internal to 1A, 1B, 1C. So, these are nodes internal to 1, and then we try to build for say 2, 3, 4, 5. Okay. Instead of building up for each node inside a region independently, we try to have one entry in the routing table which will take us to that node. So, for example, if these are countries, if I think these are countries, that region 1 is say US and region 5 is say India. So, region 1 is say Somalia and region 5 is India. Okay. So, you have region 5 as Somalia and region 1 as India. So, then what we have now, only one step how to come from Somalia to India. So, say come to New Delhi, okay. And from New Delhi there will be domestic flights or domestic route. Okay. That is kept only when you, or that is discovered only when you come to New Delhi. Okay. That is discovered only when you come to New Delhi. So, now see this 1A has 1B which you go through, it is 1 hop, 1C it is 1 hop. Now, if you want to go to 2, well, how will you go? You will use 1B, you will use 1B and it takes 2 hop to go to 2. Okay. So, next is if you want to go to 3, then it is through 1C and you will take 2 hops. You will go to 1C and go 2 hops. If you want to go to a node in 4, it takes 3 hops. And if you want to go to a node in 5, it takes 4 hops. But anyway, your next hop is 1C. The next hop is 1C for all these cases. Okay. So, what are the problems, or are there some small problems which can happen? Are there some small problems which can happen? So, one small problem which can happen, just if you see that I have 1A, say I have 1B, 1A, 1C, and both are actually getting connected to two separate nodes in 2. Both are getting connected to two separate nodes. So, say this is New York and this is Bombay and this is San Francisco or Washington and this is Delhi. Something like this which is happening, that two nodes are getting connected to two nodes. So, then there is confusion that which is gateway or which should be considered as gateway, and the routing table needs to be built on one gateway. The routing table needs to be built on one gateway, or it may so happen. So, this is one another important thing about routing table which we should understand, is that as soon as we begin to use this Newark Bombay route, it may get congested. And then our link state routing may say that this is taking much more time than this. So, you may again switch. Okay. This switching, if we are going on delay, this switching may continuously occur. So, you may see a continuous hop from one end to another end. Okay. That can also happen. So, anyway, so what is essentially happening? Essentially happening is, if I now think a little more analytically or little more numerically. So, if I have just 720 routers, okay, if I have 720 routers in 24 regions, okay, 720 routers in 24 regions. So, now we try to build up 3 levels of hierarchy. So, we try to build up 3 levels of hierarchy. So, 8 clusters, each containing. So, if we have 24 regions, okay, and says there are 720 routers and each is distributed equally, say each is distributed equally, then how many each table will have how many entries? Each table will have how many entries? Say there are 720 routers and 24 regions. So, each region has how many? Each region, how many nodes? 720 by 24, 720 by 24, 30. Okay. So, 30 means each node has 29 internal neighbors. So, each node, so there are this way maybe many regions. So, this way you have how many regions? 24 regions, and each has 30 nodes. So, then each node has 29 internal neighbors, and how many external neighbors? One from each region. So, how many regions are there? 24. So, there will be 23 external neighbors. So, then how big will be the routing table? The routing table will be 29 plus 23 is 52 rows instead of 720 rows. Okay. So, that's how this is not only what is happening, you are reducing the routing table size and also dividing the internet logically. Okay. You are dividing the internet logically. So, you can actually, this is not only helping in route, you can uh, check congestion. Okay, you can check congestion, you can put firewalls. Okay, you can put firewalls. So, all sorts of things can be done. Okay. So, this is so all sorts of things can be done. Fine. So, if there is another example that it need not be one level, two levels, it can be three levels, that you can have three level regions, that 8 clusters, 9 regions and 10 9 regions of 10 clusters. So, 8 clusters, 9 regions of 10. So, this won't be clusters, 8 clusters, 8 into 9, 72 and 10 areas say. Okay. So, you have 10 areas, inside those areas you have 9 regions and these 9 regions have 8 machines inside. Okay. So, what will be the table size then? What will be the table size? If we will have 7 neighbors, okay, and we will have 8 neighboring region, 8 regions neighboring, okay, and 9 neighboring area. So, then this is 7 plus 8 plus 9 is how much? 24. So, then what is happening in the previous case? We had 52. In the previous case, we had 52. Now, we are going down to 24. So, from 719 to 52 to 20. So, this is the goodness of cluster. Okay. So, this is the goodness. So, yes, you can have, see, now the question is, uh, so now the question is, you can have more than 3 levels, you can have 5 level, 10 levels, there is no issues. But the point is that as soon as you increase the level, there are many other problems which comes. One problem I showed you, that then we have to continuously determine which are the gateways. We have to continuously determine which are the gateways, and we have to actually, that means there will be a lot of churn inside the network, a lot of churn in the routing table, which is again not very good. So, more levels, what is the flip side? More levels is more churn. More churn means what? More change in routing table. Very good. So, now we have understood what is a hierarchical routing algorithm. Okay. So, now next we talk about the broadcast part. So, broadcast is also a it's as I have told you that broadcast is in the beginning only I have told you broadcast and flooding is not same. Okay, because broadcast we are broadcasting known nodes and we know all the nodes. Now, how to do broadcast efficiently. Okay. So, the question is how to do broadcast efficiently, because you can all now understand clearly that you can now understand. So, yeah, I told you distance vector routing we are not using. There is a question I see that distance vector routing, but distance vector routing we will only use, if you remember last class I told, we will only use if the goodness of distance vector routing is it is very simple, just you are exchanging and you are getting it. It is less costly. In link state routing you have to get the entire graph and then do it. Here you are, it's less costly. The big problem is the count up to infinity. And when does count up to infinity comes? When there are failures. Okay. So, if a network is less prone to failure, then distance vector routing will work. Otherwise, you have to work on link state. Okay. So, I guess this part is clear. So, now the question is how to actually do broadcast much more efficiently. So, this question can be asked. So, one is that say I have a routing table. See, I have a routing table, sorry about this. Okay. So, let me go back and just show you a routing table. So, this is a routing table. Okay. So, this is a routing table which has, say, let me think that this is a routing table which, what are the entries of this routing table? Next hop entries. If I see next hop entry of this routing table, they are 1B and 1C. Okay. So, they are just 1B and 1C. So, now 1B is so see the first one, simple one, 1B is taking us where? It is taking us, okay, it is taking us to obviously 1B, then 2A, 2B, 2C, 2D, 2D, okay, and 5C, I see 5C. So, this is 1B's domain, okay, and 1C's domain is, let us see once more, 1C is 1C obviously, then 3A, 3B, 4A, 4B, 4C, 5A, 5B, not 5C, 5D, 5B. Okay, this is clear. So, now when I am sending, when I have a broadcast protocol say I have, see, there are two ways, two things to think, that I have discovered the entire network. So, I am broadcasting to the entire network, or I may not have discovered the entire network. So, let us think of a situation where I have not discovered the entire network. So, and I have said 1A, 1B, 2A, 2B, 2C, 2, I have only discovered this. An extreme condition, just to make you understand, an extreme condition where I have not discovered, any of these nodes, but I have discovered all these nodes. Okay. So, I have told you again that broadcast is thinking of discovered network and not the entire network. Okay. It is not a discovery phase. Broadcast is not a discovery phase. So, what will happen if this is a discovery phase? Typically, packet size will be small. There may not be data packets which will be sent, there will be control packets. So, also remember this, but when you are doing a broadcast, you will actually send data packets, and so the discovery is done, and say wrongfully, just wrongfully, we have just discovered this much, 1B, 2A, 2B, 2C, 2D, 2C, 5. Okay. So, then what will happen? So, now what will I do? So, if I have discovered this much, so if I again go back to the routing table, in the routing table, if I see, or if I go to this picture from, okay, let me draw this, did I draw this picture once? Okay, let me draw this picture and then you will understand the thing a little bit, that from 1A, to A, to B, to C, to D, and see this. Okay. So, now what will happen? Now, all the nodes, all the nodes to which broadcast has to be done, all the nodes to which broadcast has to be done is now telling what? You go through 1B. So, all the nodes through which broadcast has to be done is telling that you have to go through 1B. So, then your routing table would actually only activate 1B. So, the entire thing, so what you now you write in the routing table, say in a broadcast routing table, which is again wrong, I mean there is no broadcast routing table, but it will be written the packet. So, say 1B the entire set, like in the routing table 1B you go to this entire set. Now, entire set 1 will go where? Here 2A. The first hop is 2A. So, now if you think of 2A's routing table, if you think carefully of 2A's routing table, how will 2A's routing table come? So, 2A will take some nodes through 2B and some nodes to 2C. So, which of this will go through 2B and which of this will go through 2C? Let us think. Okay. So, say let us think. So, 2B will go through 2C. Okay, 2C will go through 2C. Now, 2D may go through 2B and say 5C also goes through 2D. So, let us assume that this is a faster link. Okay. So, now you have the table that from 2A there are two entries, from 2A there are two entries, one is to 2B where 2B, 2T, 5C will go and another is 2C where just 2C. So, now you are actually using the routing table and pushing the packets, but in a broadcast way. It is not the packet is not going to a single node, but it is going to multiple destination. Now, next you see it will go to 2B. So, 2B is 2B and then from 2B it will go to 2D. So, if I am going to 2B, I reach 2B. So, next hop 2D, what are the two things will go? 2D and 5C. And the next hop will be 2D and what would be the next thing? 5C. So, this is a single entry and this I reach and then slowly it also becomes a single entry, and once it becomes a single entry we finish. So, what is happening? The broadcast algorithm is acting efficiently. The broadcast acting efficiently, what it is doing? It is actually manipulating or rewriting, reformulating the routing table. Okay, it is reformulating the routing table and accordingly sending packets. So, this is again we are writing it as multicast, or you can write it as broadcast, whatever it is, that slowly you are, this is for so slowly you are building the spanning tree, or slowly you are building the router table, and ultimately each packets are going through one. Okay, fine. Okay. So, the other way of doing these things is perhaps a spanning tree. So, you can also build up a spanning tree. So, I am assuming that all of you know spanning tree. So, spanning tree is nothing that if you have a graph, the tree, a tree which, what is a spanning tree? If you have a graph, a tree which covers all the nodes. If you have a graph, a tree which covers all the nodes, but it is still a tree. Okay. So, what is the advantage of a tree? Advantage from network perspective, that packets will come through a single node, because it is a tree structure. If I start from one node, it will, and if the tree structure is rooted to a node, so spanning tree rooted at say node n. Okay. If I have a spanning tree rooted at node n, so what is the advantage? That all nodes in the network from that node n can be reached through one unique path. Okay. Or in other way, you can say that all nodes will receive a packet from an unique node. Okay. All node will receive a packet. If the packets are flowing through those network, all nodes will receive a packet through a through a through a unique node, okay, or unique, say we can say unique predecessor. So, what is happening? All nodes receive packets through unique predecessor. Okay. So, then what happens? But spanning tree is a logical concept. See, spanning tree is a logical concept, because ultimately if you see this graph, okay, if you see these nodes are actually physically there. These nodes are actually physically there, but spanning tree is a logical concept. You can build up a spanning tree on this graph, but you cannot simply see, you do not have here E and H connected, but you cannot simply throw that connection. That connection will anyway stay. So, since spanning tree is a logical concept, okay, so how do we in practice implement spanning tree? So, the question stays that in practice implementation of spanning tree, I guess you are understanding or appreciating the issue, that we always just build spanning tree and do flooding, but the others are not going. So, that we have to think carefully. So, then we have we have to store a bit more information. Okay, store a bit more information, and what information you have to store? That from each node, okay, you have to store a bit more information, and what information you have to store? From each node, which is the preferred path, preferred predecessor. This you have to store in each node. In each node, you have to store this information, that which is the preferred predecessor. And if any packet comes from any other node than the preferred predecessor, then what do you do? Discard. Simple discard. So, let me tell you this way. So, say this is the graph. I will take a simple thing. Okay. So, this is say a graph. Okay, and A, B, C, D, E, and rooted to A, this can be a spanning tree. It cannot be, it may not be the optimal spanning tree, but this is a spanning tree. Okay, A, B, C, D, E. This is not the minimum spanning tree or maximum spanning tree, but this is a spanning tree. Okay. Now, what happens when you are at E? This connection is still there, its connection is not this connection is not. So, E has this information that any packet which comes for D is legal, and any packet which comes from anybody else than D is illegal. Okay. So, anybody else than D here is B. So, if a packet comes from, so A is sending up, A is doing some sort of broadcasting, send it to B, send to C, C is sending to D, D is sending to E, but B is also, B does not know, okay, B does not know. So, nobody knows their next hop thing, that which are their legal next hop, which are not their legal next hop, that they do not know. Okay. So that would, if they knows that, then that would actually make a big thing, because there can be multiple legal next hops. Okay. So that would actually make, you have to make an entire routing table then. So then what is happening, the B sends to E, but E understands that this is not a legal thing. So immediately E will discard. Okay. So then how many maximum number of uh, such so this is a wastage. So this is a wastage surely. So what would be the number of wastage then? So number of wastage. So I have a graph, okay, where there is V and E, okay, V number of nodes and E number of edges. So if I have a V number of nodes, if I build up a tree, how many edges will there be? It will be V minus 1. Okay, it will be V minus 1. If it's a tree, is V minus 1, and there are E edges. So how many maximum wastage it can be? E minus V minus 1. Okay, maximum wastage. Okay. So this is another way to do broadcasting, where you are optimizing on the wastage, that you are uh, seeing that there is not too much wastage. Fine. So broadcasting, I guess you have understood. Now let us, so with broadcasting, then there is multicasting, there is any casting, I am not going into this. Okay. And then there is routing for mobile hosts. So all sorts of things which you can do and know. So there are two other class of routing which I will do next class. One is the ad hoc routing, which is important. Okay. And also routing in peer-to-peer networks. Okay. Routing in peer-to-peer networks, because these are a little bit different, which I will do in the next class. But now let me just go to some more practical understanding of routing. So what is happening ultimately? What is routing? Ultimately we are doing routing through IP, and routing is internet scale. Okay, we are doing routing through IP, and routing is actually internet scale. It is not that routing is local. Okay. So we have two sorts of routing, uh, understanding, that we have this uh, internetwork routing. So an internetwork routing we have told, but let us say it more formally, that one is interior gateways. So there are gateways. So how we can think of internet, that there are autonomous systems, or and from one autonomous system to another autonomous system we are going through gateways. So there are, say, autonomous systems, and through one autonomous system through another autonomous system we are going through gateway. Okay. So then there is two types of protocols which we do. Interior gateway protocol. So within an autonomous, then again this is an interesting thing, since we are doing internet scale or world scale, that means it won't be only technical thing. There are many other things which we have to consider. Political thing, I will come to this political thing. Okay. Or means the geography we have to consider. So we have to consider various other things. Okay. So when we do internet gateway protocol, which is called IGP, interior gateway protocol, which is called IGP. So we have interior gateway protocol, interior gateway, this is IGP, and we have the border gateway. So this is border, is real border, whatever we do in border we can have border gateway protocol. Okay. So, border gateway protocol and internet protocol, the interior gateway protocol. So, interior gateway protocol is typically a an interior gateway protocol's basic algorithm is OSPF. And what is OSPF? I have told just before. What is OSPF? OSPF is link state routing at the core. Okay. So, interior gateway protocol is OSPF and OSPF is link state routing at the core. Okay. So, then let us just think carefully and write this thing, that you have autonomous systems getting connected throughout the internet, and within the say you have the IGP, interior gateway protocol. Okay, you have interior gateway protocol, and when you have interior gateway protocol, what is happening? You have interior gateway protocol, and this is OSPF. Okay, this is this standard algorithm or popular algorithm is OSPF. Okay, and OSPF works on link state routing. Okay, basic principle is link state routing. Clear? Now, when we go to BGP, border gateway protocol, what are the things which, so I have told about distance vector routing, that what are the, and we have more, what is the reliable flooding, how frequently route. So, after every 10 seconds they are checking. So, it may not get updated very fast many times, but there is a continuous check actually after every 10 seconds. How do we decide routing only best for? So, yeah, now we are talking about internet scale. So, internet scale LSR has 1. So, let us think that LSR has 1. Okay, fine. So, the other questions I will take next class, but let us just uh, see the what is BGP. So, BGP puts various type of rules, because BGP, once it is not only a technical protocol, it is also a political protocol, commercial protocol, all sorts of things it has to see. So, some constancy, no commercial traffic for education. So, if you have a education network like NKN we have, so we cannot have advertisement of say Paytm inside NKN. So, those type of protocols has to be, those type of uh, constants has to be supported by BGP. Or when you are sending data, you never put Iraq on route at Pentagon. So, if you are sending a data from US say to Dubai, so Iraq may be a good, means if I just think from uh, link state routing or from any distance vector routing, that this is the shortest path, but it is not uh, secured. It is not secured. So, BGP takes care of that. So, you can put all these rules in BGP, that when you are configuring, please even if it costs more, you you do not choose Iraq, or there can be other things that you choose cheaper network. So, cheaper network. So, if I am buying a network service say in India and buying a network service say in Bangladesh, so the network service in Bangladesh may be a little degraded, but it may be much cheap. So, all these considerations are taken, that it is not only you need the best network, but you may need the cheaper network, okay, or you may need better performing network, whatever. So, you can actually define rules that what type of routing or what type of connection you want. So, that is what is BGP protocol, and this is a very in all sorts of things. So, you can see I have actually drawn a, means I have taken from the book, but a small way, that you have various type of routing policy. Then once you build this, you build up a lot of advertisement. Again, you do a advertisement to understand or optimize the routing. After you put the constants, you put an lot of advertisement to put the routing path. Okay. So, this is all about routing, the initial routing, but routing if we do not talk about the IP protocol or exactly how IP works, then this stays incomplete, which will come back in the next class and talk. Okay. Thank you very much.